Hello and welcome to my session, Hyperscale Distributed NAT System and Software Engineering. Hi everyone, my name is Hiroki Shirokura. As a software engineer, I've been working on Line's private cloud called Verda. My main tasks include designing and implementation of private cloud network services as well as reliability engineering. Also, I made contributions to open source software that Line's network infrastructure will use. Today, I'm going to talk about designing and implementation of cloud network services. In particular, how Line has developed a name address translation, in short NAT, mechanism that is optimized for our own private network while achieving high availability and scalability. There are many Line services that run on our in-house developed private cloud Verda. We launched Verda in 2016 based on OpenStack, and now it offers Nover, Neutron, and other basic components of OpenStack, as well as additional service components shown here. Currently, Verda offers over 70,000 virtual machines, so VMs, and bare metal machines in total. These figures have surged over the last several years. The VMs have increased by 10,000s every 6 months. As the trend will continue, we will have to contain more and more VMs. To achieve this, we've designed a very simple network infrastructure. This is the closed network that Verda hypervisors connect. The hypervisors contain VMs and directly advertise routes using BGP, which builds a full layer-3 network. And we do not use VXLAN or other overlay protocols. This approach has greatly helped us to create a simple and high-capacity network infrastructure. However, simplicity has caused issues too. First, this network consumes many public IP addresses. As this was designed to be as simple as possible, there is no cloud network gateway that enables instances to connect to the internet, so we need to assign public IP addresses directly to instances. Also, enforcing fine-grained network policies is not possible. So far, the coarse-grained access control list applies to the entire infrastructure. As the size and the variety of Line services has increased, these two issues have started to matter. So we wanted to introduce the NAT feature, which terminates user connection at the gateway and allowing us to use public IP addresses more efficiently. Also, we wanted to support fine-grained access control. Against this background, we recently launched the Internet Gateway Service. When we've developed this, we've set 4 major requirements. So I would like to go into talk about this briefly. First, fair balance. With the NAT, the multiple hosts share one public IP address and a port range, but this shared space is finite. Thus, we need to set the traffic limit for a single host. For example, even if this VM transmits abnormally many packets, we need to ensure that the other 2 VMs will be able to establish connection without any troubles. Second, the flexibility. The Internet Gateway Server should be flexible enough to allow projects to tailor configuration. For example, Project A VM will use a public IP of at 142.8.01, whereas the Project B VM will use 142.8.02. A public IP address could be used solely by a single project or jointly shared by multiple projects, so there are many use cases to support. Major public cloud gateways often allow users to configure NAT for each virtual private cloud or VPC subnet. However, the Verda does not offer VPC, so we needed to design the service in a way that NAT can be configured for each VM. Third requirement is extensibility. Verda launched with a very simple architecture However, due to an increase in services, it is now expected to offer more advanced features to meet various needs. In some cases, we will face the necessity to add features on a later date. For example, applying your fine-grained network policies I mentioned earlier. So to achieve that kind of architecture, we needed to design an extensible service architecture from the beginning. The first requirement is, as the session title says, Hyperscale. As I said earlier, Verda has more than 70,000 instances. The Internet Gateway Service is expected not only just handling such a large amount of instances, but also to be hyperscalable. However, as NAT is a stateful network feature, Hyperscale is a challenging requirement. From now on, I would like to elaborate this point. First, I would like to give an overview of large-scale NAT or carrier-grade NAT that is often used by IPS network enablers as well as telecom companies who operate public networks. This approach requires very expensive vendor appliances set up to an active standby redundancy. Please look at this pair of nodes. The active node shares NAT sessions and the current state with the standby node over the dedicated interface used for synchronization. Normally, the active node handles all traffic, so the node on the left. But in case of maintenance or equipment failure, the sync link detects such trouble or any motion. Then, the standby node becomes active automatically and provides continuous network connectivity. As the two nodes have been synced in advance, you can switch the active standby nodes gracefully. But this configuration has issues too. Most critically, it has an enormous impact of a maintenance or outage. So if a switchover is triggered here, it will affect all NAT users. Although a graceful switchover is appreciated, having a large blast radius is not ideal for a hyperscale environment. You might be thinking about limiting the impact by preparing multiple clusters with 2n redundancy, but it will increase the operational costs. In addition, we need to prepare and manage L2 networks to switch traffics on the fore and the background of NAT. It would not be ideal for the L3-only network, as we prepared it in order to simplify the underlying network. So our NAT mechanism is expected to have a single scalable cluster with n+1 active redundancy and to be compatible with the existing simple L3-only network. So if we can create a hyperscale NAT system meeting these two requirements, it will be optimal. So from now here, I would like to explain how we've developed such an optimized mechanism. We've first created a new distributed NAT technology called FabricNAT that we've adopted as the backend of the Internet Gateway Service. FabricNAT can meet our two requirements, an n+1 active redundancy and a high level of compatibility with the L3-only network. Furthermore, we can achieve a FabricNAT by simply combining BGP, policy-based routing, and IBRP tunneling, which are all commonly used network technologies. Now I would like to show you how FabricNAT works. In this example, here this VM tries to access this external service. Assuming that NAT rules have been already set for each VM. As shown in the table, we have the rules to translate these three addresses. Please take a look here. Even though these three VMs share one public IP address, you can set the traffic limit by assigning a port range per VM and implementing static isolation. Using these NAT settings, the fair balance requirement can be satisfied easily. Setting the session limit per user is a very similar approach as MAP-E defined in RFC 7597. And next, please take a look at Worker. As shown here, each client has a corresponding node. Then we set the NAT rules to the Worker node. For non-Worker nodes, configure policy-based routing to redirect the traffic to the Worker node. Once you've set the routing rules for these three addresses, tables look like this. Also add some settings on the VMs that use NAT. So create and add an RBIP tunnel device and override the default route with the tunnel device so that the VMs using NAT will access to the internet with the IP tunnel. I would like to stop talking about configuration here for now, so before elaborating the SDN mechanism and the control plane, I would like to now show you how packets are forwarded. So now let's imagine this VM at 10.0.01 is going to forward a packet. At the first step, a TCP packet bound for the external server is generated on the VM. This packet matches a default route in the routing table, so it will be encapsulated in an IP bound for 10.99.0.1 and forwarded to the closed network. As each data plane node advertises the route to 10.99.0.1 using BGP, this packet is being forwarded to one of these nodes, so this is a typical anycast routing. In this case, D plane 3 receives this packet. Then the D plane 3 decapsulates the IP packet and applies the raw packet from the PBM to its PBR table. So based on the table, D plane 3 redirects the packet to D plane 1. To do so, the packet is encapsulated in another IP packet again, and it will be forwarded to D plane 1. Once the packet arrives on D plane 1, it will be decapsulated. Now, source NAT is performed. Then, the source address is translated to the public address. And with the IP forwarding simply, the packet will be forwarded to the final destination. Now, the packets from the VM arrives on the original destination. This is an example of an outgoing connection. So with the policy-based routing, the packet is redirected to the worker based on the source field of the packet. Conversely, for an incoming connection, a packet will be redirected to a worker based on IP destination and a port destination instead. But in this case, therefore, the PBR tables will change like this. The packet flow is the same as the previous one, so I'm not going to illustrate, but now it is clear how packets are sent out using the two sets of a PBR. So to recap the basic routing mechanism. When configuring FabricNAT, we assign a port range to each client, so that session quota of each client would not be consumed by other clients. We elect a worker node for each client and distribute the NAT rules accordingly. As the nodes do not sync sessions to each other, we can ensure a high level of the scalability against the amount of sessions. As we've distributed the NAT routes, we need to pass the traffic from a client to a correct worker. For that purpose, the two-step routing is in place, namely BGP routing and PBR that can achieve a symmetric routing. Now, you might be wondering if the N+1 redundancy is achieved or if the blast radius is limited. So let's see what happens if a node is overloaded and goes down. The packet flow that I explained earlier is now represented by this line. If I add 2 more lines to describe traffics from other VMs, it looks like this. But no, it's very confusing, so let's simplify the diagram. First, within this flow, Look at this path. The packet is first forwarded from VM to 10.99.01 and then redirected to its worker node, so dplane 1. Before forwarding, with any case, a traffic can be routed over any of these multiple passes. That means no matter which dplane received the packet will be routed to dplane 1 anyway. As the traffic is stateless and the multiple active passes are available, we can interpret this diagram in this way. Now I extend the line to the external server. I do the same things for the same two lines. The diagram looks like this, but now it's very clear. If dplane 1 goes down suddenly, it will affect only one VM, as shown here. That means the blast radius is 1 over n, and other VMs will be able to maintain connectivity. This is the case even if you have increased the VMs that use NAT or added dplane nodes. For example, this FabricNAT cluster has 8 dplanes. Even if dplane 4 goes down, it will affect only one VM, which means the blast radius is 1 over n again. Now you'd have a better picture of the advantages of FabricNAT. It performs routing in 2 steps, so dividing tasks into 2 parts to offer the NAT service to clients. First, it offers multiple stateless active paths to make the network robust enough. And the second step, it actually performs a NAT. Although this process is per state, the blast radius is limited to 1 over n. Unlike carrier-grade NAT or other conventional approach that has achieved the graceful fault tolerance with a large blast radius, we prefer a hyperscale architecture with a limited blast radius. As new stateless application layer protocols and reconnection mechanisms emerge, modernized solutions are available for infrastructure. So in future, maybe we would adopt a graceful mechanism to improve the maintainability, but it will be on the next phase. Now I would like to go back to control planes that I've skipped before. As I've explained the routing mechanism that the FabricNAT uses. Next question is, how do you configure it? As the Internet Gateway Service has an SLO of 4 nines or above, so we need to configure clustering and distribution in an efficient and robust way. Therefore, for the clustering of the dplane nodes, we've adopted Console. That is a very popular open source for service mesh. For configuring distributed routing on data planes, instead of a remote procedure call, we've decided to use etcd, a famous distributed KVS, and manage configuration declaratively.
Now I will explain the SDN mechanism with an example when a user newly configured NAT to 10.0.0.4 VM. Let's first realign these blocks like this and assign software components to each block. This is Console's server and client to build data plane cluster. Console agents operating on dplane use a gossip protocol to check what nodes exist in the cluster. This is etcd cluster, which manages NAT configuration as a distributed key value store. On each data plane, a microservice called NATlet is operating and watching etcd cluster to check NAT configuration, so it can detect updates whenever new data is written or changed in the etcd cluster. Also, Console is monitoring watch API of Console agent. The monitoring watch API of Console agent so that it can adjust configuration according to events such as cluster failure, addition, or deletion of new node. Another microservice called scheduler also watches etcd just like NATlet and elect a worker node according to NAT configuration and overwrite the setting. And lastly, this API server receives NAT configuration via REST API from user of Internet Gateway Service and reflect NAT configuration to etcd according to a request. With that, the picture now looks much clearer. Again, let's look at how this responds to a user request step by step. From now on, I will explain SDN mechanism with an example when a user newly configured NAT to 10.0.0.4 VM. First, user calls REST API to get NAT configuration for 10.0.0.4. Then, API server reserves a port range for a new NAT rule. To avoid overlaps with other NAT rules using the same public IP, API server newly calculates and secures the port range. Then the NAT config field with the preserved port range will be written to etcd. Scheduler detects that NAT configuration was newly written to etcd. When worker part in NAT config is null, it elects a new worker and asks console server for data plane cluster information to schedule NAT config. As I explained earlier, console server retains information in the cluster by using gossip protocol. The cluster information is notified to scheduler. Scheduler checks worker information from the cluster information it received and picks healthy clusters. Among the selected clusters, ones with less worker counts will be sorted out. In this example, deep lane 4 had 0 worker, so this is elected as a new worker. At the end, scheduler overrides the NAT config with the worker field being filled into etcd. With that, you have successfully completed database register from NAT scheduling. Lastly, I will introduce you how to configure routing for each data plane. NATlet watches etcd, keeping an eye on new entry of a scheduled NAT configuration. When scheduled NAT configuration is written, NATlet receives it with context. Each NATlet checks the received NAT configuration, and when the NATlet is not a worker, just like the deep lane 1, 2, 3 on the left, policy-based routing configuration will be added to redirect worker. This diagram shows only a rule for redirecting to the Internet communication to worker, but in fact, redirecting from the Internet communication will be configured as well. In that case, just like the earlier packet flow, destination IP and port will figure out PBR path for redirection. When a node is a worker, it configures NAT. Then all the necessary configuration is done. FabricNAT routing is now available. Now that we have covered control plane SDN mechanism, here's the recap. When FabricNAT is connected to a distributed system, each component will not use RPC, but instead apply decorrelative configuration watch and self-reconciliation, enabling each component to loosely connect with each other to navigate the overall configuration. This respects Kubernetes design principle, and SDN is designed based on that. Also, by leveraging open source software, which supports cloud-native technologies such as Console and etcd, it simplifies implementation of distributed system and brings down the development cost. For example, currently, deep lane node failure detection mechanism is offloaded to Console. Console cluster continuously monitors and connects to nodes to check whether every node is kept participating in clusters. That is what Gossip Protocol is about. Suppose a certain node connectivity becomes unstable or invalid, other agents in Console cluster can recognize it instantly. Scheduler also watches Console. So it can detect that deep line 1 went down and take the NAT configuration where worker is set as deep line 1 to override it right away. A new worker is elected in the same way as the normal procedure for configuring NAT, and NATlet catches what was changed in etcd and adjusts its configuration accordingly. When developing important features for distributed system, rather than doing everything within a small group of developers like us, utilizing open source software which has large user base and continuously maintained, it's helpful to reduce development cost and ensure overall stability. Next, let's take a look at software stability. Similar to FabricNAT, there are many systems out there which has its own unique mechanisms. They're not just made of out-of-the-box open source software such as console and etcd, but also consisting of original components developed fully from scratch, just like NATlet scheduler and API server in our case. Then how stable is each process? Which one is more stable than the other? Less matured software obviously requires frequent upgrades. Take NATlet and etcd as an example. Right after a release, which one needs to be restarted more frequently? The answer is obvious. NATlet needs more restarts. If this service was operating for a decade with periodic maintenance, many bugs and undefined behaviors would have been fixed along the way. Every proprietary service was immature at the beginning. etcd and console may not need to be upgraded so often unless there is a critical security patch required. On the other hand, NATlet and scheduler may need to be upgraded relatively more often. We were well aware that a newly minted software is prone to break, so that we focused when we designed the whole distributed system was making it easier to restart and upgrade anytime. If you had to develop a software that never breaks 24/7, your job is extremely difficult. But if you allow a software to be upgraded every now and then, you can significantly lower development costs as well as giving peace of mind to developers. Our proprietary components I introduced today can also restart anytime, and it's designed to be not affected by restart timing. If you're not using a decorrelated resource watch but use RPC to configure distributed systems, then you need to factor in a risk in advance in case NATlet gets restarted while calling RPC and lose critical settings, which only adds complexity to the mechanism. On the contrary, with the decorrelated mechanism to watch resource, even when a restart happened when making a change, reconciliation loop will be triggered, enabling resource to restore to a state right before the restart. Decorrelated configuration can make every component easy to maintain with less operational burden, and we can take full advantage of software engineering power. Next, I will talk about how we operate and monitor these services on a daily basis. As I said earlier, our original components can get restarted and upgraded very easily. So deployment itself is very easy too. We can simply perform deployment as well as maintenance via Ansible. Upgrade and downgrade can be performed by just changing image ID of a component, in this example, an image ID of Docker, and then run a playbook again. Like this, every component is encapsulated by a container or similar things so that it can easily determine specific states at a time of errors or failures. We have 3 types of monitoring. First is monitoring basic metrics. We simply adopt 2 patterns. The one is to monitor metrics by integrating to console, and the other is use Kube state metrics. I can say that this is a very simple monitoring design. In addition to that, our Internet Gateway service also runs external monitoring by employing two robot concepts to monitor automatically from user's perspective. The first robot is dynamic robot. This robot simulates user experience from the point of configuring NAT to getting user connected. About 32 of user simulated virtual machines are already created in each region where Internet Gateway service is deployed, and they check behavior of Internet Gateway service by Ansible from different places simultaneously. For example, issue OpenStack token first, use the token to configure NAT to itself, then the robot tests external connection to check whether a right public IP and port range are connected. The external destination is a simplified HTTP server we built, and there you can get the source information. Then a response with that information will be returned to the robot. Robot can then confirm whether the response matches with the external connection already configured to itself. At the end, NAT is deleted to restore to the original state. And if you do the same things to multiple hosts at the same time, you can check whether user experience is correct from the point of NAT configuration to establishing connections. But this alone cannot confirm whether existing users are kept connected properly. That is why we have another robot. That is the static robot. Static robot also prepared multiple VMs with NAT configuration in each region, similar to dynamic robot, to check whether connections are maintained by using black box exporter. Initial settings of a static robot is set up by Ansible. Status of static robot's communication is checked in the same way as dynamic robot. And this metrics is collected by Prometheus via console. As you know, a periodic self-check mechanism of user experience on a software level will allow you to thoroughly gauge KPIs of your service. That is about what we have done so far. Lastly, let me also talk about our next steps and future work. The first is access control. As I explained about our issues at the outset, we control access from clients based on allow list. But now we are considering to provide a control method not based on ID such as IP addresses or port number, but controlling based on name like example.com. Part of UTM features is name-based access control mechanisms such as URL filter. But this is difficult to control communication in an environment like CDN, where IP address changes dynamically. As we also control DNS inside our private cloud, we are taking advantage of that to handle dynamic environments with an aim to implement FQDN access control by client using NAT. Next is operational efficiency. We currently upgrade or restart components manually by running Ansible. But we want to run it automatically based on events such as alerts from a monitoring platform. We have to reduce operational tasks as much as possible. Otherwise, we wouldn't be able to spend enough time on software engineering. In order to save time for supporting additional services in the future, we are always exploring opportunities for automation. As I explained earlier, components' flexible restart capability actually benefits automation effort. When we designed that capability, we factored in a future aim of automatically running weekly rollout of nodes so that we will be able to proactively maintain our service rather than taking actions after the fact. Another future plan is private zone. In the linedevday 2019, we introduced SDN mechanism to enable network isolation with SRv6. We are working on to move this to a next step and officially release VPC-like mechanism in our private cloud, Verda. The private zone not only provides network isolation, but also contains network gateway resource, just like Cloud Router, which works as a virtual router for terminating and routing user communication. We are planning to apply the Internet gateway I talked about today to this private zone. And not only that, many other features, including VPN gateway, are also in our roadmap, so they are a required VCP. Here is the summary of my presentation. Our private cloud, Verda, debuted with a simple architecture, but that introduced us a challenge of offering more complex network features to accommodate the rapid growth of the line services. Part of the solutions to that challenge was to release Internet Gateway, our proprietary network service. With the Internet Gateway, we developed a new distributed NAT mechanism called FabricNAT to support Hyperscale NAT service, enabling high scalability and failure resiliency. SDN mechanism for FabricNAT makes use of cloud-native technologies such as console and etcd, as well as declarative configuration model like Kubernetes. And as a result, we can restart components easily when necessary. That concludes my presentation. We continue to try to think outside the box and always taking up a challenge and look for optimal technology that best fits our private cloud. That is how we support the infrastructure of the entire line services. If you want to know more about our work, I'm happy to take questions from you after the session. Thank you very much for watching.